This is Lesson 26 in our Calculus 2 series, Areas and Lengths in Polar Coordinates. In this lesson, we learn to compute the area of regions bounded by polar curves, as well as the arc length of polar curves. Remember that in Cartesian or rectangular coordinates, we approximate areas using rectangles, and we take the number of rectangles to infinity. So for example, if this is our curve and the pink shaded area is the area we are trying to find, we approximate using rectangles by subdividing the interval on x. And then we take the number of rectangles to infinity. And keep in mind here that we're subdividing the interval on our independent variable. So in polar coordinates, our independent variable is theta. And so we are going to subdivide the interval on theta and make approximations to start. So if this shaded area is the area we're looking to find, which in this case happens to be the area bounded by r equals 1 plus cosine theta as theta goes from 0 to pi, we divide the interval on theta into subintervals. And we're going to approximate the area over each subinterval using circular sectors. So we need to figure out how to find the area of a circular sector of radius r and angle theta, or delta theta as it will be in this case. So how do we find the area of a circular sector? Well, we know the entire circle has theta equals 2 pi and the area is pi r squared. So if we have a sector of the circle of angle theta, so we're talking about just a sector of the circle here of angle theta, let's call its area A, and then we'll set up a proportion. For the angle of 2 pi, we have an area of pi r squared. For an angle of theta, we want to solve for this area A. So solving for A, we get A is equal to theta pi r square over 2 pi, which simplifies to theta r square over 2. So for a circle of radius r, the area of the sector of angle theta is theta r square over 2. So let's see how we can use that. For our area approximation, the angle of each sector is delta theta, and that's given by beta minus alpha over n. So these are the bounds on theta, and we're dividing that difference by n. And we're going to use a circular sector with radius f of theta I. So here we see theta I, and then f of theta I is the r value here, it's the radius value. And so we're going to approximate the area of the ith sector using that radius. And so using the formula theta r square over 2, the area of the ith sector in this approximation is going to be delta theta times f of theta I quantity squared over 2. So we can write that as 1/2 f of theta I quantity squared delta theta. And so the total area is going to be the limit as n goes to infinity, the summation I goes from 1 to n, of the area of the ith sector. And so the area of the ith sector we said was 1/2 f of theta I quantity squared delta theta. And then as n goes to infinity, we recognize this as the definite integral 1/2 integral alpha to beta of f of theta squared d theta. And so this is the formula we're going to be using. The area enclosed by r equals f of theta as theta goes from alpha to beta is equal to 1/2 integral from alpha to beta f of theta squared d theta. Now let's take a look at an example. Sketch the graph of r equals 2 sine theta and find the area it encloses. So we know the interval for area is going to be this integral here. We know that r equals f of theta, so in here is going to be 2 sine theta. We just need to know what the proper bounds alpha and beta are on the angle theta. And once we sketch the graph, we'll be able to figure out those bounds. So please pause the video and work on that. To sketch the graph, we're going to start with r equals 2 sine theta graphed in rectangular form. So here we have r equals 2 sine theta, where this is our theta axis and this is our r axis. And now we want to translate this information into a polar graph. So we notice here that we have theta equals 0 and r equals 0. So theta equals 0 is in the direction of the positive x-axis, and r equals 0 means we stay at the origin. Now we see that as theta increases to pi over 2, r increases to 2, and it reaches its maximum value of 2 at theta equals pi over 2. So as theta increases, r increases to 2. So the radius increases and it reaches its maximum value of 2 at pi over 2. Then, as theta goes from pi over 2 to pi, the radius decreases back to 0, and it reaches 0 when theta is equal to pi. So now we're decreasing this radius, and it reaches 0 as theta equals pi, which is in the direction of the negative x-axis. And we've completed the graph here, because we realize that for theta between pi and 2 pi, we're repeating the same set of points. So we realize that theta is going from 0 to pi for this graph. And so 0 is going to be alpha, and pi is going to be beta, the bounds on our integral. And so our integral is going to look like this. 1/2 integral from 0 to pi of 2 sine theta quantity squared. Remember, this is f of theta squared. So simplifying here, we're going to have 4 sine square theta. We could bring that 4 outside and simplify it with the 1/2. And so that gives us a 2 on the outside. And then the sine square theta we're going to replace with 1/2 1 minus cosine 2 theta. And notice we can simplify the 2 and the 1/2, and so we're left with this integral. And so we integrate, we have theta minus 1/2 sine 2 theta going from 0 to pi. And so that's equal to pi. And if we change this graph into rectangular coordinates, we would recognize that this is a circle of radius 1 centered at 0, 1. And it's a circle of radius 1 tells us that its area would be pi times 1 squared, which is equal to pi. So we did get the area that we expected. Let's take a look at another example. Sketch the graph of r equals sine 2 theta and find the area it encloses. So it's a very similar problem, but now we have the 2 in a different place and our graph is going to look very different. So again, we want to sketch the graph, and so with that we'll be able to find the proper bounds on theta over which to integrate, and then we'll compute our integral for area. So please pause the video and work on that. Again, we're going to start our sketch with our function graphed in rectangular form. So here we have r equals sine 2 theta, where this is our theta axis and this is our r axis. Note that this 2 here is the frequency, and so that makes the period for this graph equal to pi. Remember that 2 pi over the absolute value of this number is going to give us the period. So that's pi in this case. So now let's translate that to polar form. Again, we're starting with theta equals 0, r equals 0. Theta equals 0 is the positive x-axis. R equals 0 means we stay at the origin. Now, as theta goes from 0 to pi over 4, r goes from 0 to 1 and reaches its maximum value of 1 at pi over 4. So pi over 4 is in this direction. Here's a radius of 1, and that's going to be achieved at pi over 4. So we have our radius increasing to 1 as theta increases from 0 to pi over 4. Then, as theta goes from pi over 4 to pi over 2, the radius decreases back to 0. As the angle goes from pi over 4 to pi over 2, our radius goes back to 0. Now, as theta goes from pi over 2 to 3 pi over 4, the radius goes from 0 to negative 1. So as our angle goes from pi over 2 to 3 pi over 4, our radius values are all negative, going from 0 to negative 1. So at 3 pi over 4, we have a radius value of negative 1. At 3 pi over 4, we have a radius value of negative 1. So that means we have to go back in this direction, and that would be about here. So for the angle values between pi over 2 and 3 pi over 4, the radius values are negative, and they're getting more and more negative towards negative 1. So we're here. And as theta increases from 3 pi over 4 to pi, the radius values are going back to 0. They're still negative and going back to 0. So now for these angle values here, we're getting these radius values going from negative 1 to 0. Now, we've completed this for the period that we showed here, but notice that we still have angles on our polar graph that we didn't talk about yet. We didn't talk about angles from pi to 2 pi here. So we need to continue this graph in rectangular form out to 2 pi and then follow along the graph in polar coordinates. So now we're here. As theta goes from pi to 5 pi over 4, as theta goes from pi to 5 pi over 4, our radius goes from 0 to 1. So our radius is going from 0 So our radius is going from 0, increasing to 1. And as theta goes from 5 pi over 4 to 3 pi over 2, here to here, our radius is decreasing from 1 to 0. Now as theta goes from 3 pi over 2 to 7 pi over 4, as we're going to 7 pi over 4, we're getting negative radius values, going from 0 to negative 1. So at 7 pi over 4, we have a radius of negative 1. So when we're at 7 pi over 4, we're going backwards, we have a radius of negative 1. It's about here. So for these angle values, we're getting negative radial values going from 0 to negative 1. And then from 7 pi over 4 to 2 pi, going from negative 1 to 0. So for these angles, going from negative 1 to 0. So now we're here, and we want to find the area enclosed by this graph. So we have two options. We realize that in this graph, theta went from 0 to 2 pi to cover the entire graph. And so we could set up our integral as 1/2 integral from 0 to 2 pi of sine of 2 theta squared d theta. We could also notice that there's symmetry in this graph. And we could take the area of just one petal and then multiply that area by 4. We could recognize the area enclosed by the graph as being 4 times the area of one petal. So that would be 4 times 1/2 integral 0 to pi over 2 sine of 2 theta quantity squared d theta. Both integrals will give you the correct answer. So let's continue and solve here. 4 times 1/2 is 2. Replacing the sine 2 theta quantity squared with a 1/2 1 minus cosine 4 theta, we're here. And then the 2 and the 1/2 can cancel. And we integrate, plug in our bounds, and we're at pi over 2. And as an exercise, you can try the integral going from 0 to 2 pi, and you'll see you'll get the same answer. Let's take a look at another. Sketch the graph of r equals 2 cosine theta minus 1 and find the area of the inner loop. Please pause the video and work on that. Again, we start with a sketch in rectangular form. So here we have r as a function of theta graphed in rectangular form. This is 2 cosine theta minus 1. So we have a cosine graph with an amplitude of 2 and then shifted down 1 unit. So we're here. We see that when theta is equal to 0, r starts at 1. So when theta is equal to 0, facing the positive x-axis direction, r is equal to 1. So we start here. And then as theta increases to pi over 2, r decreases to negative 1. So we should find out where r is equal to 0 here. So we set r equals 2 cosine theta minus 1 equal to 0 and solve for theta. So we get cosine theta is equal to 1/2, which over this interval we know happens at pi over 3 and then at 5 pi over 3, which is in quadrant 4. So we know that at pi over 3 we have a radius of 0 and at pi over 2 a radius of negative 1. At pi over 3 a radius of 0 and at pi over 2 a radius of negative 1. So for angle values in here we have negative radius values, which means we'll be in here, and at pi over 2 we have a radius of negative 1. And at pi over 2 we have a radius of negative 1. Now as theta goes from pi over 2 to pi, we continue to have negative radius values. So for these angles we're going to be in the 4th quadrant here with our radius values, and those radius values go from negative 1 out to negative 3. So at an angle of pi we're at negative 3. So when we're looking in the negative x-axis direction, when theta is equal to pi, we have a radius value of negative 3. So we're here. So our radius values are going to get more and more negative as theta increases. And then as theta goes from pi to 3 pi over 2, we continue to have negative radius values, but they're increasing to negative 1, going from a radius of negative 3 to a negative 1. So at 3 pi over 2, we have a radius of negative 1. So when we're facing the negative y-axis, that's 3 pi over 2, we have a radius of negative 1. So we're here. Now we're going from negative 1 to 0 as theta goes from 3 pi over 2 to 5 pi over 3. Right, that's what we found here. So 5 pi over 3 is here, and as theta goes from 3 pi over 2 to 5 pi over 3, we're going from negative 1 to 0. From 5 pi over 3 to 2 pi, we're going from radius of 0 to radius of 1. And so that's our graph, and we're looking for the area of the inner loop. So we need to find the interval on theta that covers the inner loop and only the inner loop. Now we know the radius is 0 when theta is equal to pi over 3 and 5 pi over 3, but we need to be really careful here. If we put the bounds on our integral as 5 pi over 3 and pi over 3, we're not going to get the area that we're looking for. Because remember that the integral from 5 pi over 3 to pi over 3 is really negative of the integral from pi over 3 to 5 pi over 3. And this is the area enclosed by the outer loop. So really, this integral is going to be negative of this area. And that's not what we're looking for. So we need to recognize these bounds on the inner loop either as going from negative pi over 3 to pi over 3, or we can recognize the symmetry in this inner loop and take 2 times the area from 0 to pi over 3. Those are our options there. So let's compute this one, because I like 0 angles better than I like negative angles. So the 2 and the 1/2 will cancel, and then we want to multiply this out. Now to integrate a cosine square theta, we're going to have to replace it with 1/2 1 plus cosine 2 theta. So notice this 4 times the 1/2 we get here is going to be a 2. And so we get 2 times 1 plus cosine 2 theta there. And we still have the negative 4 cosine theta plus 1. And multiplying this out and simplifying, we have a 2 here that adds with the 1 here, and that's going to give us 3. And then we have 2 cosine 2 theta here. And so then we'll integrate and plug in our bounds. And we get negative 3 radical 3 over 2 plus pi. Now let's take a look at finding the area between polar curves. So if, for example, we have r equals f of theta, that's greater than or equal to r equals g of theta, we could talk about finding the area between these curves. And when I talk about f of theta being greater than g of theta, I'm talking about it having larger r values, which means it goes further away from the origin over this interval. So how can we find this area? It's a similar idea to what we did in rectangular coordinates. We would want to first find the area enclosed by f of theta over the given interval, and then from it subtract the area enclosed by g over the same interval. So the area between r equals f of theta and r equals g of theta for f of theta greater than or equal to g of theta over the interval alpha to beta is equal to the area enclosed by f of theta minus the area enclosed by g of theta over that interval. So we can combine these into one integral, keeping the 1/2 on the outside and squaring both f and g before we subtract. So now let's find the area inside r equals 2 sine 2 theta and outside r equals 1. Note that the graph of r equals 2 sine 2 theta is very similar to the graph we had earlier of r equals sine 2 theta. The only difference is now, because of this factor of 2, the petals reach a maximum radius of 2 instead of 1. So please pause the video, graph these curves, and shade the region. And then we'll talk about finding the interval over which to integrate. So here's our graph for r equals 2 sine 2 theta, and r equals 1 is the circle. And so the area that we're talking about is inside r equals 2 sine 2 theta, but outside the circle. So we're talking about these 4 green pieces. This is what we're trying to add up, this area. So in order to find this area, we need to find the theta values for which the curves intersect. So we want to set 2 sine 2 theta equal to 1 and solve for theta. 2 sine 2 theta equals 1 gives us sine 2 theta equals 1/2. And so 2 theta, the angle here, must be pi over 6 plus an integer multiple of 2 pi, or 5 pi over 6 plus an integer multiple of 2 pi. So these are our solutions for 2 theta. So dividing both sides by 2 says that theta is going to be pi over 12 plus pi k, or 5 pi over 12 plus pi k. So that tells us that the first 2 intersection points we have here are pi over 12 and 5 pi over 12. So integrating over these bounds is going to get us the area of one of these green pieces. And we can recognize the symmetry here and multiply that integral by 4 to get the area that we are looking for. So our area is going to be 4 times 1/2 the integral from pi over 12 to 5 pi over 12. Here's f of theta quantity squared minus g of theta quantity squared. So our outer function is 2 sine 2 theta, that goes here. Our inner function is r equals 1, that's here. We get 2 pi over 3 plus radical 3. And that's the area we're looking for. Now let's take a look at one more topic, arc length of polar curves. So now we want to find the length of these polar graphs. And just as with slopes, we want to regard these polar curves as parametric curves by thinking of x as r cosine theta, or f of theta cosine theta, and y being f of theta sine theta. And so the length of r equals f of theta using the parametric equations would look like this. But finding dx d theta and dy d theta from here, squaring them and simplifying, we realize that dx d theta squared plus dy d theta squared equals dr d theta squared plus r squared. So here for dx d theta, we use the product rule to get what's inside the parentheses here. dy d theta, same thing, use the product rule here. And then we're just squaring out, combining like terms, and making use of our trig identity, sine square theta plus cosine square theta is equal to 1. So we used parametric curves to derive this formula, but when you're solving for arc length of polar curves, you can go straight to this formula here. So let's find the length of the cardioid, r equals 1 minus cosine theta. Now notice here, they're not giving us any bounds on theta, so we're going to have to examine the graph of this function to find the proper bounds on theta. So that's our cardioid, r equals 1 minus cosine theta, and we realize that we covered the entire graph from 0 to 2 pi, and so those are the proper bounds on theta. So remember that inside our radical we're going to have r squared plus dr d theta squared. So r is equal to 1 minus cosine theta, and then dr d theta is then positive sine theta, so that goes here, sine square theta. And so now to integrate, we'll see if we can simplify what's under the radical. Multiplying out here, we have 1 minus 2 cosine theta plus cosine square theta plus sine square theta. And that's great, that gives us a positive 1. So now we have 2 minus 2 cosine theta. Now using trig identities, we can replace this by a 4 sine square of theta over 2. And this isn't quite as obvious, so you might not have thought of that on your own, but let's go through the work here. We know that sine square x is equal to 1/2 of 1 minus cosine 2x. And so when we see a 2 minus 2 cosine of something, we think maybe we can make some relationship between what we have and this equation here. Now notice that we have coefficients of 2 here, not coefficients of 1/2. So we want to multiply both sides of this by 4. That's going to give us a 2. 1 minus cosine 2x is equal to 4 sine square x. So now we're almost there, but what we have here is a theta, not a 2 theta. So theta is going to replace 2x, which means this x is then theta over 2. So now we have radical of 4 sine square theta over 2 in our integral. And we recognize that sine of theta over 2 is greater than or equal to 0 on this interval for theta, because that means we're looking at sine of 0 to sine of pi. And those are values that are greater than or equal to 0. So we can do our simplification by canceling the radical and the square and not having to worry about the absolute value. So we're here, and we integrate, and we get an arc length of 8 units. And with this, we'll conclude our lesson on areas and lengths in polar coordinates.